our warm-up today, we have this differential equation. Kind of start focusing on it, get that into your brain, because we're going to be referring back to it throughout the day. So, in order to solve this, when you move your y terms to this side, it makes it easier if you clean up the compound fraction first. So I rewrote 1 over 1 minus y over L as L over L minus y. And then once you got that, you have a lovely case for partial fractions. So when you do the partial fractions, did you all get 1 and 1 for A and B? How do we get the partial fractions? Okay, so I'm having board issues today. I have to hit the thing every time it changes. Okay, so we have 1 over y times L over L minus y. And we want it to equal A over y plus B over L minus y. Does that make sense? Okay, so then you multiply through by the LCD. So you end up with L equals A times L minus y plus by. And then you can plug in any value you want to solve for A and B. But if you, let's see, yeah, so if I group, I'm trying to think of the best way to do it. I do it by grouping. If I plug in a 0 for y, I get L equals A times L, and so then that just means A is 1. And if I plug in an L for y, I get L equals B times L, and then B is 1. So that would be your easiest way to go. All right. So then there's your equivalent there. And then it's just natural log. The most common mistake that I saw today so far, for people that really did work through this, was getting from here to here. Because from here to here, the antiderivative 1 over L minus y, be very careful. We've been getting so knee-deep in heavy integrals that some of us have forgotten our basics, which is to remember to divide by that coefficient, right? So if this was L minus 2y, we'd have a negative 1/2 out here, right? L minus y, we have that negative 1 in front. So make sure you don't forget about that, because that changes the whole thing if you don't have that negative. All right, and then you just, there it's just kind of doing some algebra. I found another little difference in how my former students, how I have approached solving differential equations and how our other calculus teacher has approached it. And I just want the students who did not have me last semester to know that I'm fine. Either way is totally fine. I personally rewrite my constant whenever it gets modified. So, for example, this is e to the kt times e to the c. E to the c is not the same thing as c, so I don't feel right just writing c when it's no longer c. It's e to the c, so I replace it with a new name and I call it a. And then when I drop the absolute value and have that plus or minus on this side, which gets absorbed into yet another new constant, which I call m, I like m because then you have me, right? I love this because you have me and mine. So anyway, so I change constant names. If you just do C, 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 I won't mark you off. It's like, all right. So anyway, so you get all the y's on one side, factor, divide, and then from here to here, why would we want to go to here and not just use this one? This one looks nicer, right? It's nice and simple. This one just doesn't. But this is the one that's the standard form, and this is the one we're going to be using. And one of the main benefits of having this guy in the format that it is that our L now is isolated on top. And so it's really easy to write an equation if you know L. To go from here to here, you just divide by n e to the kt. Every time. And then 1 over n becomes b. So, where is all this taking us? This is a roadmap of how to get from here to here. And in the future, for these problems, you are going to need to be able to, number one, recognize problems that are presented to you in this format, and then be able to go from here to here. Now, the optimum method would be to not have to do all of this every time. So I'm actually going to encourage you to memorize this, rather than having to sit there and re-derive it every time you need it. Okay? And I've got them in the next slide, or in a couple slides. So today we're doing logistic equations. These are called logistic equations. This is section 6.3. We're back in chapter 6 for the last time. So today we'll be able to recognize them, graph them, and solve them. First, we're going to explain them. So, to generate a traditional growth model describing population, we started with the knowledge that the rate of growth of the population was proportional to the population at a given time t. So you end up with this dy dt equals ky kind of a thing, and when you solve it, you get essentially PERT, right? Which we called y equals c e to the kt. Is that what you guys called it before? Okay. All right, so anyway, this is your standard population growth for continuous exponential growth, right? The problem with continuous exponential growth is that most populations in reality can't just continue to grow exponentially forever. If the human population continued to grow at an exponential rate forever, right, eventually we would overtake the planet and then everything would explode, right? So, so anyway, no, but there's limiting factors on populations, right? You have to have food and water and space and, you know, all this stuff that you need to survive as a population.
What if we started getting our energy from the sun?
So anyway,
Technically,
so the limit, this upper limit is called L, and its technical term is called the carrying capacity. Carrying capacity. So, people have mentioned they've heard this before. Have you guys heard this before?
yeah.
Biology. Oh, good. Okay. All right. Let's see. So we're relating.
I'm ahead of you.
All right. Good. The new growth model that incorporates this limiting condition is called a logistic differential equation, and is written like this. All right. So this is called the logistic differential equation, and it models population growth with a limiting factor. Where L is that limiting factor. All right, so this is a rate, right? dy dt. This is a rate of growth of the population, not the actual population. It's the rate. Yeah, we're going to get to another screen that kind of summarizes. All right, so hey, we've already solved this equation, right? So if you know the rate, you are permitted and encouraged to jump to the solution. So this is your rate, this is your amount, right? Rate of growth of the population, population at any time t. I would know both of those. The more you use them, the better you will learn them and be able to recognize them. You won't die if you accidentally don't recognize it and solve it from scratch. You just have to be able to solve it, right? Okay, so anyway, I mean, if you had to go from here to here, you can do it, right? It's not terribly hard, it's a, a little partial fraction integral that you have to solve. Okay, so whenever you have this, you can assume that. Everyone have both of those written down? Wait.
Uh-oh, write them down.
Don't look, camera, don't look.
K equals 5.
L equals 1,000.
Okay. So, just to kind of give you an intro, to make sure you know how to match things up, I'm gonna erase this too. Okay, so our first one, we've got a rate of change of a population, is modeled by this function right here. I want you guys to take a second and see if you can figure out K and L. Just kind of match it up with the formula that you've got, and see if you can find K and L. Whatever you prefer for your study and review.
K is 5.
All right. Carrie, what'd you get for K? 5. Does everyone agree is K 5?
C.
C. C. Ka, K. I don't remember K in Spanish. Is it ka? Ka. Kai. Is single? Okay. See, I say okay all the time, so I really should be saying oka.
No, they say okay.
Did they really?
Yeah.
Okay.
Oka.
I literally just got it.
Oka.
No, it's pronounced Oki.
What?
Alright, so Liam,
Are you break?
what's that? One
have 4 vision,
okay? Okay, so that means that this population has a maximum value of 1,000, right? So now, could we write a model for the actual population? So ignore this bottom part, they're not related.
Yes.
So, and that looks like 1,000. So anyway, so take a second and see if you could go from here to the actual population model. You'll have a B in your answer, that's okay.
Negative K. Oh, yeah. Yeah.
So just leave it in terms of Y and T and B.
So to solve for B, do you have to be like given a
You'd have to be,
point?
yeah,
Be a legend.
which we will be doing.
You're a legend.
You don't have to be a legend, you just have to have
You have to be Brian then though.
True.
You have to be grinded in, yeah.
Like that Jack Brian.
Yeah, like when. When you,
Patagonia?
what?
I haven't seen it yet.
Is it new?
Is it new? Yeah, it's actually brand new. Got it
It's
yesterday.
in,
I like it. I like it.
I think it's gonna be Tuesday.
Looks good.
Oh, that's been such fast.
What?
Yes, Jay.
Those brands, I don't know.
So,
I love it.
I know.
how's that top? 1,000. All right, guys, back on track. Back on track. Focus. Okay, 1,000. That's your limiting factor, right on top. L, big, bam, done. Right? All right. What goes on the bottom here for all of these? Jack?
What?
1. 1 plus, right? Good. And then, do we know B?
No.
No, so B
No,
stays.
not it.
Yeah, that's okay, keep going. All right, so now we have an e to the negative 5t. All right, so that's the big thing, is being able to go from this to this. So if you can write your K and write your L, and then just plug them into the new model. Right? All right, so now let's pretend you started with. Okay, let's pretend you started with this. See if you can find K, L, and see if you can figure out the initial population.
Oh,
I'm not that.
that's tricky.
Zero, so you have 1, so then 6.
Dude, we got.
That was 10.
Wait, she gave us B.
So it's whatever 6666 is.
Oh, yeah, you're right. Because T is
Oh, should I try B too?
It's
Might
6,
as well.
6, 6, 6, 6. Okay, like 4 6s divided by 11.
No, actually, it's not 4 6s. It's 6,666. 4 6s would be 24.
Or in other words, it's a double.
Yeah, come on, man.
Yeah, come on.
Yeah.
Wait, so that first equation's in
The number was
606.
606?
The original equation is like the initial population, right? Like the dp or dt.
The
No, that's the rate.
DPDT, that's your
Oh,
rate of
it's the rate.
change of your
Oh.
population.
The
Okay.
initial is when t is 0.
Ah, I
Yes.
see, I see, I see, I
Yes.
see.
Actually, wait, no. Even the zero. So 6, 6, 6, 6.
Wait, yeah, 0, 666 divided by.
7.
Or is it? Ah, yeah. Okay, guys, quiet down. K is just 0.3. That negative is part of the formula, so be careful about that.
Does it even matter?
Yeah, this is, I'm sorry that I'm having trouble lighting right to the issue. Okay, so show me guys what's L?
6, 6, 6, 6.
6, 6, 6, 6. Very good. All right, let's see. Bigisha,
Yeah.
how you doing?
Good.
What's B?
10. Look at that. Oh, chill.
All right. Tommy, how's it going? Oh, did you want to be called up? I'll call you on the next one. All right, so let's see, how do we find initial population?
Well, you can find or you set up the other equation first, and then you can tell that if you plug in 6, 6, 6, 6, then it would just be, as the growth would be 0, so then it would the initial population be.
Or you could just set t equal to 0.
Oh, initial population just means the population at time 0.
Oh, yeah.
Yeah, so we're just gonna find P of 0. But it's very good, actually what you were talking about though is something that we're gonna be doing soon.
Okay.
So it's not a bad train of thought, right?
Step
All
ahead
right,
of the game.
so P of 0,
He's too smart.
everything's visual, everything. Okay, 6, 6, 6, 6 divided by 1 plus 10 e to the 0, which is just 1 plus 10, which is 11. Does anyone know what 6, 6, 6, 6 divided by 11 is?
606.
Apparently so.
Zero.
Okay, good. All right, let's just talk graphs for a minute. I haven't seen any problems yet. That doesn't mean they don't exist, but I haven't seen any in my looking throughs yet of past BC exams to find any one where you had to actually graph a logistic equation. However, you have to do it in your homework, and it's a good thing to kind of know what the shape looks like because it helps you understand the limits, and you will be asked about limits. So, the graphical logistic equation has a general shape that looks like this. So it's got 2 horizontal asymptotes, the lower limit and the upper limit.
Actually.
Most of the time, the lower limit of a population is 0, right? Not 100%, but most of the time, right? If you can't have negative population unless you have zombies, right? Yes, okay. So, yeah, so most of the time it's 0. And then your upper limit is whatever the upper limit is, right? So then you've got that other horizontal asymptote. All right. The change from the lower horizontal asymptote to the upper horizontal asymptote, you get this little whoop thing. And the center of that is a point of inflection. This inflection point, this inflection point is found, the x value of it is ln b over k. Not ln of the quantity, but just ln b divided by k. And then, of course, it's half of L because it's halfway between 0 and L. It would be the y value. But the x value is the one that's kind of tricky. So you don't have to memorize that, but it will help make graphing faster and easier if you are aware. So,
Oh.
anyway, ln b over
I
k.
like the two.
Dude, you gotta say that. Doesn't Thomas
Yes.
teach you?
What would be the integral of 1 over degeneris d degeneris?
Okay, so it's ln degeneris plus c.
Well, that
Ryan! That was cold.
Beat in 2017.
ln degeneris plus the c would be like, I don't know, does she do any shows where she's in a boat?
Oh, wait,
Oh,
what?
yeah, Oh, it's 100% Dory. The answer to that is Dory,
Okay, thank you.
right?
Okay.
Because it's Ellen DeGeneres plus the C. She's Dory.
Oh, jeez, I was not even going
She's
there.
a fish. Hi, Nemo. Okay. All right, good. All right. So let's walk through a couple of example problems. So first, a state game commission releases 40 elk into a game refuge. So that's their initial population. What's the initial population of elk? 40. Good. After 5 years, the elk population is 104. The commission believes that the environment can support no more than 4,000 elk. Write a logistic differential equation for the growth of the elk population. This, you don't have to solve for anything. It's just writing the original setup of the model of the differential equation, the actual like D. I did dy dt, but you could do dE for elk or whatever. Okay, so everyone write that.
Okay.
What's K again?
The rate at which it grows.
You don't know K yet, so you can just use KK.
Okay.
Okay.
Oh, good one, Cole.
It was like a snap thought.
Correct.
Oh yeah. Do we know why?
Y stays Y. Yeah, basically. But you need to know how to do it.
Wait,
That's
L
the
is the starting rate.
L is the carrying capacity.
growth model, right?
So, oh, 4,000.
There you go. Look at that.
Okay, Ross.
We have one for Tala and the teacher. And it's from Jason.
Jake also.
Alright, should we turn the camera off?
No, we're not even on. It's on. We're gonna. I got you. We're gonna. Can I zoom out? I'm gonna zoom out. Brian, tell them. Brian, I zoom out, Miss Price. Miss Price.
I don't
Miss
know.
Price,
I don't
can I
know
zoom
why
out?
the girls don't like me.
We're really good.
It's dressing. I got the sheets on the floor, nothing on me. And I can't take it no more, it's 100 degrees. I got 1 foot out the door, where my keys? 'Cause I gotta leave in the back of the cab. Until the driver hands down, give it up fast. I got your body on my mind, all of that. Oh, just the thought of you gets me so high, so high. You're the one I want to want me. And if you want, then oh, you've got me. There's nothing I wouldn't do, to have next to you. Even if we're big ones, I want to want me. Even if you're wrong, then oh, you've got love, you're not alone.
I'm gonna stand by you. I'll be your eyes when yours can't shine. I'll be your arms, I'll be your steady satellite when you can't rise. Well, I'll crawl with you on hands and knees, 'cause
I'm gonna stand by you. Even if we're breaking down, we can find a way to break through. Even if we can't find heaven, I'll walk through hell with you.
love, you're not alone. 'Cause I can't help
Falling in
love with you.
Happy Valentine's Day.
Dumb mark. Dumb mark.
Very good. That is so awkward.
J. Cole.
Alright.
I zoomed it out for you guys. I like zoomed it out. Perfect. It's good. It's perfect.
They are what they are, right? Okay. So, wait, did y'all understand how we got this? Yep. Okay, so now what we have to do is write a model for the elk population in terms of T only. So what that means is you're going to want to write your basis for your population model. Start with your y equals and fill in what you know, right? Then you're going to use the other information given to see if you can solve for what you don't know, right? Which would be B and K. I would start with the initial population first. So there you go. Get to work.
1 plus negative T.
Not a good day for me. Oh, it's negative K5. 5K.
No, negative
That's for 5.
You just write the equation first.
Oh,
And then you set for how many you set y equal to 40 and change or T equal to 0 because then it cancels out the K. So then you can find B. And once you know B, you set it equal to 104 and K.
Plug in the initial 40 to get the
Hold on, Mark 2017.
J. Cole.
Yeah, J. Cole.
You know what?
Do you know how to start? We're starting with, you have to.
But you know what y is? So y is 40, t would be 0, t would be 0.
Okay, so, you want this, you know L.
That's probably better than my idea. Setting it equal to 104.
L is your limiting factor.
5 for T.
Remember, if you look at
I haven't seen Marty's yet. What's Marty's? You guys seen
That's the
that?
one with I don't know if it's the one with
Marty's?
I don't know, is that one good?
They're all.
No, but like all of them have like
Or Kimball's. I haven't seen Kimball's.
These.
You didn't backflip in it.
Yeah, he didn't see backflip in classes that he had room to, so like I saw him twice, one time he did, one time he didn't. No, the funniest part was
I
he
think
goes,
it is, but I don't want to talk out my mouth.
Backflip in our class. It's funny.
It is the other
Stories of life.
What?
The story had it.
probably right.
Just ranking.
That's the first time I think I've seen all of them. I've seen like 8.
I've seen Hotline Bling,
24.
the group with like
I haven't seen that one. Is that the one with Annabelle?
it's decent. Yeah.
I haven't seen
That
that.
one was good, yeah.
I've seen and that's the one with Mike Swanson.
Yeah, that one. I saw that one. That was okay. It was okay. You bought them?
Yeah, I bought the one.
Why?
What do you mean you bought it? Oh, okay.
4K. That was the one with Penn, right? That was good.
And like George Conn.
Yeah. No. No, it wasn't. No. That was the one with Ricky.
And Grant.
Woody Ayers.
I've seen that one twice.
Yeah.
What they say?
Like Justin Bieber and oh yeah.
Okay.
Wait, what was that
There's
one?
like a Justin Bieber.
It was as long as you want me drag me down. Yeah.
So the one that's actually the hardest to describe, someone was asking me what do the B and the K actually represent? And so I looked it up just to see if they really did represent anything. The K really does. Yes!
No, Brian, hold up.
Can of white?
Oh yeah.
Hey. Bring him back out.
Who's that?
Ryan,
Have you gotten him yet?
no, I haven't.
Is this your first one?
Wow, Hannah, you have a lot of admirers.
Ted's zooming out.
It's like,
Quiet, please.
Oh, I just wanna take you anywhere you like. We can go out any day, any night. Maybe I'll take you there, take you there. Maybe I'll take you there. Oh, tell me how to turn you on. You can get anything that you want. Baby, just shout it out, Baby, just shout it out. And if you ding, 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 ding. Ooh, under the light, ching 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 down, ching 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 heart. Just one look and ching 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 ching. Fell in love with ching 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 girl. Feel my heart tonight. Just one look, yeah. Waiting for a girl like you. Do. Get out, get out of my heart and fall into my arms right inside. I don't know what it is that I need, darling. You got that one thing. Whoa, baby, look what you've done to me. Go, baby, look what you've done to me. Baby, I'll never leave if you keep holding me this way. Na 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 na. Let me kiss you.
That wasn't me.
Okay, back to logistic growth functions. Oh, wait. Okay.
Anthony started listening. It's like,
Oh, Hannah.
and
Hannah,
He zoomed on your face.
Hannah. I got your face on there.
What I found, the only thing that I found to explain the B and the K is that this is the A, they have it written as A is like your B. So they said that the limiting value of C, which is our L, is 1 plus A times larger than the initial output. So if we took the initial value, multiplied it by 1 plus B, we would get C, which makes sense because you plug in a 0 for T, right? That's the only thing that they have. And then they have nothing to explain really the K apart from saying that if it's positive, then your function will increase. If it's negative, the function will decrease. So there's not much else to it. So there's not a really good way of describing what do B and K represent, apart from the fact that K, if you plug in a 0 for T, then you get this plus this times Y equals your initial population. Anyway, so there you go. Now, by the way, especially students who are not from my class, make sure you keep K exact, not rounded, especially with population problems. And one of the things I noticed on your take-home quizzes this past week, you are not giving me 3 full decimals. You have to give every answer to at least 3 decimal places unless it specifies otherwise. That is the same on the AP exam. They do not say it in front of any problem. They say it, where do they say it, my students? Anyone know? In the instructions, right? So if you open your booklet and read through all those paragraphs, somewhere in the paragraphs it'll say, by the way, all answers have to be rounded to at least 3 decimal places, right? So make sure that you do that. So from here forward, you guys all have to give me at least 3 decimals every time. Yes?
So why why does the College Board make the instruction thing so long?
To tell you everything you need to know.
But shouldn't they just give us like,
Brian did.
Yeah, I know, man.
Ooh, or is there? Okay.
Oh wait, no.
Ah, okay, because remember, our formula is L over 1 plus B e to the negative kt. So since I got a negative value for k, it ends up canceling with the other negative and becoming positive. Is that okay? Unless you put the negative up and have L in a 1287 over 47. Then it'd be negative.
Yeah.
so if the population is growing, K will be negative?
Positive.
Positive.
But isn't this population growing?
This is positive, believe it or not. Just because there's a negative in front doesn't make it negative.
Oh, yeah.
Right? Why is this a positive number? Because whenever you have a natural log of a number less than 1, the output is negative, right? So believe it or not, this k is a positive number. If you were to sit there and put it in your calculator, you'd get positive. All right. So graph, quick sketch of the graph. So there you go. Anyone remember how we find the x value of this point of inflection?
Something.
Okay. Now, the limit of the population model as t approaches infinity, you should be able to just do this in your head in a moment. But you could also do it analytically as well. The clock stops.
No.
Yeah, the clock stops.
Probably
But it didn't make the noise. The noise is what I really
No,
need.
it's fine. All that shows is that time froze.
Okay.
Yeah, we're
All
not
right,
allowed to
good.
learn. Time's
Fourth period,
frozen.
I'm loving that this is the lesson that's getting recorded today. So, let's get back on track. So, does anyone have an idea for the limit as t approaches infinity? How did you get 4,000?
Because that's our L, which is,
Yeah, because if you just look at the graph,
and
right?
they explained first that they don't think we'll go over 4,000.
There you go. Yes, beautifully
Hannah
said.
White,
So,
2017.
4,000 is your limiting factor, your carrying capacity. So 4,000 is the limit as t approaches infinity. If you do this limit analytically, by actually like plugging an infinity in for t, I want you to be very aware, and this brings us back to the whole is k negative thing. Whenever you have a natural log of a number less than 1, the natural log output is negative. So this becomes e to the negative infinity, which is why it ends up this number goes to 0, right? Because you end up with 99 over e to the infinity, which basically approaches 0, right? So your limit is 4,000. If it was a negative, which ended up being a positive, if you ended up having like 99 times e to the infinity, you'd have 4,000 divided by infinity, which would be 0, right? So that would be a population decay kind of a model. But this is a population growth kind of a model, so it approaches 4,000. Or, you could also say the limit is 4,000 by the Caury-Saturnus method. Okay? So I learned yesterday afternoon what the Caury-Saturnus method is. So Caury-Saturnus was a student here a number of years ago in Mr. Thomas's class, right? So he used to make his students do this every time, right, for the limit. And so she said, well, goodness, if the limit exists, and I want you to think about this for a second, if you have a logistic equation, for any equation, it doesn't even have to be a logistic, for any equation, if the limit as x approaches infinity exists, it means that the function has to flatten out there, right? Because the limit has to be one y value and only one, right? If it didn't flatten out, then it doesn't exist because it's approaching infinity or negative infinity or oscillating, right? So for the limit to exist, the function has to flatten out and become basically horizontal at one specific y value, right? So if the function flattens out at a y value, what would the slope have to be? 0. So if you have any limit as x, or in this case t, approaches infinity, and you are only presented with a differential equation, think to yourself, well, if that limit exists, that means that the slope has to equal 0. So you set this equal to 0 and you say, well, I either get that y is 0, that would be this horizontal asymptote, the limit is t approaches negative infinity, or I get y equals 4,000. And that's your other limit, right? So, oh, the hands are up. Yes, Glenn?
How would you know which one is which?
Thought.
You know the bottom.
Yeah, I don't know, you'd have to think about it for a minute and just kind of figure it out.
Yeah.
But this one is a growth model,
Oh, what if it doesn't
so
start at
everything is positive. Although you in this, like if you were just given this with no k, you wouldn't know if it was growing or decaying. So they, decaying. So anyway, they would have to, they'd have to tell you. So anyway, we'll do more Kari-Saknus models as well. Yes, yes, you may. All right, so going back in time a little bit to the year 1991. All right, this is a no calculator question. This was on the 1991 BC exam, problem number 6.
A certain rumor.
A certain rumor. Who knows what the rumor is? A certain rumor spreads through community at the rate of dy dt equals 2y times 1 minus y, where y is the proportion of the population that has heard the rumor at time t. What proportion of the community has heard the rumor when it is spreading the fastest? Now, this first part doesn't really deal with the whole point of it being logistic. We'll get into that in the next part. But this first part is actually, when you hear the word fastest, what do we think of? We think of a max, right? So we are actually, now remember, this is the rate that the rumor spreads. We want to know when the rate spreads the fastest, right? So we're looking for a max of the rate. Using any method you want, take a moment and see if you can figure out when this rate has a max.
So just take the derivative. No, you take the derivative of the derivative. And then
Feel free to talk to each other.
That makes sense. Cold.
As long as you're working on this.
No, yes, you have to actually drive.
you're not looking at
That's
Oh, right, yeah. Oh, you're right. Why'd you get that? I didn't work one half.
Oh, that's.
2 times 1 minus y. Did you remember that?
I got one. Yeah.
Take
Write it like that.
Yeah.
Get you on that side.
Yeah, then you had.
So just distribute.
Cold.
That makes it
I
easy.
that.
Yeah.
4, 6, 4, 2. Cold. You gotta have.
Well, the other
2y.
But then you